Hi everyone, my name is Bangzhi Liu. I am a staff member at Penn State Nanofabrication Facility working on FESM and atomic layer deposition. Currently, I'm working partially for MCL using FIB to prepare FESM and TM samples. Today, I'm very happy to have this opportunity talking about the strategies for better cross-sectional imaging, comparing two basic methods, edge cleaving and FIB. Cross-sectional SEM view is often needed for applications like coating thickness measurement, process verification, and failure analysis. So what is edge cleaving first? This is a simple way how I make the sample by pressing hard on the edge of a sample using the back end of a tweezer till the sample cleaves along the direction pressing down. Then you can mount the sample vertically for SEM imaging. This method is often used inside our clean room since it is quick and easy. It does not cost you anything, and oftentimes it makes a very good sample. Next, I'm going to show you some SEM images obtained using this method. This sample is an acid grating made of silicon from Dr. McIntyre's group. As you can see, the edge cleaving gives you a very clean cross-sectional view of the grating and allows you to do very high resolution imaging. This sample is a hafnium oxide coated complex zinc structure made by Dr. Teresa Mills' group about 10 years ago. The hafnium oxide coating was prepared by thermal ALD. ALD is known for conformal coating with atomic precision. This cross-sectional sample was prepared to evaluate the uniformity of ALD hafnium oxide coating. Again, you can see the edge cleaving does a very good job in showing you the amazing coating uniformity. The 20 nanometer hafnium oxides follow the silicon surface all along very well. A little bit heads up right here. Since I have been working on PVD and ALD for a long time, many examples below are related to evaluation of coating uniformity by different techniques, including E-beam evaporation and sputtering deposition. You can get some ideas about the pros and the cons of different deposition techniques if you are interested. Now, I would like to show you an example when edge cleaving does not work well. This sample is nitride coated indium phosphide device. The nitride film cleaves very well, but not the indium phosphide substrate. This example is the opposite case. The silicon substrate and the oxide layer cleave very well, but not the platinum layer. Non-refractory metals are usually very stretchy. The film can get damaged when cleaving. This platinum layer was deposited by E-beam evaporation. The peeling off from the substrate indicates the adhesion between platinum layer and the substrate is very poor. In summary, edge cleaving works well on silicon, oxide, and nitride, but may not work well if the substrate or film is ductile metal, or if the material does not cleave straight, or cleaving involves damage to either the substrate or film. Speaking of damage, a common mistake I have seen from users was trying to break the sample by bending. This actually will introduce more damage to the sample, so please try avoid bending to minimize damage when cleaving the sample. When edge cleaving does not work, we have to think about some other method, for example, FIB. This method has been widely used in semiconductor industry for site-specific applications. FIB is commonly used to make TM lamella by milling two sides of trenches, then leaving a thin slab of material for TEM observation. Using FIB to prepare cross-sectional SEM sample is much simpler. Only the first few steps are involved. A carbon protection layer is deposited first, then mill just one side of trench, followed by low KV cleaning. The whole process takes about 1 to 1.5 hours. But before going to FIB, let me show you another edge cleaving example. This sample is very similar to the last sample, but this time, the platinum film is deposited by sputtering instead of E-beam evaporation. In this case, edge cleaving did a decent job because platinum film stick well to the substrate, even though certain stretching damages can be observed. This cross-section view still allows us to measure the film thickness accurately. I took the same sample to FIB and milled a one-side trench to expose the cross-section of the film. Now you can see much better details under LPSEM. You can make more accurate measurements of the film thickness, and you can even see the grain structure of the film. In this case, FIB is definitely better than edge cleaving. Now let me show you a site-specific example. This sample is a patterned PDD sample with platinum dots on top from Professor Susan McKenty's group. The electrical measurement failed in this region, and the students would like to study what happened underneath the platinum electrode. I milled a one-side trench across the platinum boundary. This is what I got. I was amazed by the details I could see. This is the PTT stack. This is the sputtered top platinum electrode. And this is the low temperature platinum bottom layer on top of PiO2. You can see the platinum intruded into the PTT stack. You can see voids in both PTT stack and the low temperature platinum layer. One thing concerned to the user the most is something going on right here. Maybe silicide formation leading to device failure. This is a very interesting sample from Professor Lin-Xiao Zhu's group for quantum packaging application. The student would like to bond two different substrates, InGaAs and the silicon, together. He deposited gold film on both substrates, then put them face to face inside a vacuum chamber, then apply heat and pressure. This is the condition. After bonding, I broke the sample apart using edge cleaving, since it is easy and quick. Well, you can definitely see some details at the interface, for example, voice, and something going on right here. I also use FIB to prepare another cross-sectional view sample. This BSE image reveals a lot of details edge cleaving can show. The grain structure indicates the two gold films bonded together very well, giving voids of different sizes at the interface due to atom migration. Now we can see clearly what is going on right here. Gold actually migrate into InGaAs substrate, leaving crocodile voids at this interface. The next example is a study I was involved using cross-sectional view imaging in evaluating coating uniformity between sputtering and E-beam evaporation on angled surface. This is a gold-coated grating done by sputtering. Edge cleaving shows gold covered both the high angle and the low angle surface very well. but on the high-angle surface, the film thickness is much thinner. For comparison, this is the FIB prepared cross-section, giving much better view and showing the film start to taper at the bottom of the valley. And the FIB cross-section view allows you to make very accurate measurement. This is a fibbed cross-section view of the E-beam gold-coated grating. The gold coating on the low-angle surface is very uniform, but on the high-angle surface, the film is very porous with columnar structure. By comparison, sputtering is better in terms of uniformity. The film thickness varies based on the angle. E-beam variation does not do well on high-angle surface. Talking about conformal coating, ALD deposition is the ideal technique to use, as shown in this last example. The left image shows you a very deep silicon trench. Both the surface and the inner walls are covered by ALD aluminum oxide uniformly, with the bottom section filled with aluminum oxide completely. The right image shows you the bottom section of a larger silicon trench, covered by an alternation of two layers of ALD deposition. The initial deposition follows the rough morphology very well and eventually smooths out the starting roughness when the film becomes thicker. Luckily, this sample is made of silicon and oxide. Edge cleaving works great, but it would be very difficult to use gallium FIB to mill such a big sample. More powerful FIB would be needed. For example, plasma FIB, which we do not have at the moment. Hopefully, we can get it in the future so we can mill large cross-section samples. By showing you all the examples, I'm hoping you can figure out what is a better way to prepare cross-sectional samples for your own application. The answer is, it depends. It depends on what you have. Depends on your substrate materials, your film material. It depends on what information you would like to have from your sample. It depends on how much money you have to spend and how soon you want to get your result. Again, edge cleaving is quick and easy. It does not cost you anything, and it may give you the information you need. On the other hand, it takes about 1 to 1.5 hours to fib a sample with added cost, but it can give you more details about your samples. Last, you also need to consider the tool limitation. Alright, this is all I have for this topic. Thank you very much for your attention. You are welcome to reach me or leave comments below for any questions.